So far in this course, we've focused on a toolkit of algorithm design that allows you to design efficient algorithms for various problems. We've also spent some time talking about important problems on graphs and how they can be solved algorithmically. We're going to switch gears in these last 4 segments in the course, because not every problem is going to be solvable by efficient algorithms. And sometimes it's important to recognize that problems are not solvable efficiently and seek to redefine the problem or do something else. So we're going to talk about efficiency in a slightly more abstract way now. So we ask ourselves, what does it mean for an algorithm to be efficient, first of all? And you've seen instances of efficient algorithms, but maybe you haven't thought fully about what the definition of efficient should be. But let's first note that the running time of an algorithm is expressed in terms of the length of the input. Basically, if you take a sorting problem or a problem of finding the minimum spanning tree in a graph, it's very natural to expect that as you have a bigger list to sort, or as you have a bigger graph on which you want to find the spanning tree, you're going to take longer. Your algorithm is going to take longer. So clearly, the running time of an algorithm grows with the length of the input. So the input length is usually designated by n when we're talking about algorithm analysis. And so we express the running time as a function of this length n. So sorting algorithms take n log n comparisons, where n is the number of numbers, which is roughly the input length there. Now, what is the input length? You have to be a little bit careful. It depends on exactly how you encode the input into a string of binary bits. Every input can be thought of as a string of binary bits. But we won't worry about the details of the encoding. Once you encode the input, you just measure its length and then express the running time as a function of that length. So when you say that an algorithm runs in order n squared time, what it means is that for sufficiently long inputs, the algorithm takes no more than a quadratic time in the input length, a constant times the quadratic time in the input length. And when an algorithm, so we say an algorithm is efficient if its running time is a polynomial of the input length. That is, it grows only as n squared or n cubed or some small polynomial. So what is a polynomial? Basically, we say that an algorithm is efficient if its running time is big O of n to the c for some constant c. As I said, if quadratic would be order n squared, cubic would be order n cubed, but even n to the 100, even though that's a terrible running time, would still be considered polynomial time. So anything where n is not in the power, but a constant is in the power, is a polynomial time algorithm. N log n is polynomial time because n log n is big O of n squared. Even though log n is not it doesn't look like a polynomial, n log n is big O of n squared, and so that's a polynomial time algorithm. Examples of running times that are not polynomial are 2 to the n, for example. That's exponential. So what does 2 to the n mean? That if you increase the input size n from, say, 10 to 11, or any number to 1 more, the running time of the algorithm doubles. So, for example, if you have an algorithm that runs in time 2 to the n, if you run it on an input of length 10, it'll take about 1,000 steps. If you run it on an input of size 11, it'll take 2,000 steps. And if you keep going, if you run it on an input of size 20, it takes 1,000,000 steps, and roughly. And if you run on an input of size 30, it takes 1,000,000,000 steps. So it's quickly getting out of hand. An exponential time algorithm is not practical to run for any n that's reasonably large, because the time keeps on blowing up. We've seen an example of a problem where you need an exponential number of steps to solve. That was not an efficient algorithm, and that was the problem of the towers of Hanoi, where we had to move a stack of n disks from peg 1 to peg 2, and that took about 2 to the n steps. Other non-polynomial running times are like n factorial or n to the log n. N to the log n is not polynomial because in the exponent you have a log n, which is not a constant. Okay, so roughly keep this in mind. Efficient is polynomial. Now, in order to talk abstractly about problems and their efficiency and what problems are hard, we actually need to simplify the class of problems we think about, just because they're cleaner to study. Simpler problems are cleaner to study. what we will do is actually look at problems called decision problems. What are decision problems? They're problems where the answer is just yes or no. A good example of a decision problem is, given a number n, is n a prime number? So the answer is either yes, n is prime, or no, n is not prime. So that's a decision problem. Or, for example, given two sequences x and y, do they have a common subsequence of length at least k, or greater than k? We solved some version of this problem using dynamic programming, but that is the way I phrased it here is a decision problem. Do they or do they not have a common subsequence of length greater than k? The answer is yes or no. Or does a graph have a path from S to T of length at most k? Again, that's a yes or no question. So these are decision problems. Now, you might think that in general our problems are much more complicated than decision problems, and we lose something by focusing only on decision problems. It turns out that you don't. So for most real problems you want to solve, there's actually an associated decision problem, and an efficient algorithm for the decision problem allows you to solve the original problem. So let me just illustrate by one example. Suppose we play this game where I think of a number, say between 1 and 1,000, and you have to figure out what my number is. And to make it a decision problem kind of setting, you're only allowed to ask me questions of the form, is your number greater than equal to x, where x is anything you choose. So for example, you can say, is your number greater than equal to 100? And I will say yes or no. So I'm solving a decision problem for you. I'm answering your decision questions, is x greater than equal to 100, say. I'm telling you yes or no. But you can see that using my ability to solve that decision problem, you can actually figure out my number, actually figure out what the number is I'm thinking of. So this is an example where the problem of figuring out the number I'm thinking of can be solved if only you could solve decision problems like, is my number greater than equal to some value? And this is going to be a repeating theme. Any problem you want to solve, you can usually find a decision problem where if you could only solve the decision problem, you could solve the original problem. So we now define an abstract concept called the class P. A class P consists of all decision problems for which there is a polynomial time algorithm. In other words, the class P is a set of all problems that are efficiently solvable. All the examples we've seen, decision problems associated with minimum spanning trees or shortest paths, and decision problems associated with the problems we solved using dynamic programming and greedy, are all examples of problems in P. Just to be concrete, what is the decision problem associated with minimum spanning trees? Well, the problem minimum spanning trees, as we studied it, was not a decision problem. It was, given a weighted graph, find a minimum spanning tree in the graph. That's not a yes-no question. But we could change it into a related yes-no question by saying, given a weighted graph and a number k, is there a spanning tree of weight at most k? That's a yes-no question. And if you could only solve that yes-no question, you can actually solve the original problem as well. You can think about how you might do that. So the decision problem of minimum spanning tree is, given a graph and a number k, is there a spanning tree of weight at most k? One more decision problem that we mentioned at the outset is, what about testing if n is a prime number? Given an input n, is it a prime number? Now, in high school or earlier, you probably learned an algorithm for testing if n is a prime number. What it was a trial division-based algorithm. Simply try to divide n by all the numbers between 2 and square root of n. If you want to be a little cleverer, you can only divide it by the prime numbers between 2 and square root of n, but we won't worry about it. So the simplest algorithm is to just divide n by every number between 2 and square root of n. If any of those i's is actually a factor of n, then you found a factor of n and n is not prime, and you can say not prime or no. And if no such I is found, so none of the numbers between 2 and square root of n divide n evenly, then you can say yes, or n is prime. So that's an algorithm for the decision problem of, given n, is it prime? It takes about square root of n steps because you're going to try dividing n by square root of n different numbers. Is that a polynomial? Well, square root of n is big O of n, certainly. But this is not polynomial time, because the input length for representing the number n is only log n bits. The input is usually a binary encoding of the number, and n is so if n is a million, let's say, about a million, then how many binary bits does it take to write down n? Well, it takes about 20 bits. That's log base 2 of a million. So in fact, the number million is represented by an input of size 20. But if you're going to take square root of n's division, square root of a million is about 1,000. So you can see that even on a 20-bit input, you're going to take about 1,000 divisions. And if you work this out, this is growing exponentially. So this is not a polynomial time algorithm. Actually, I should add that after much research and a lot of hard algorithms and analysis, we now know there's a very sophisticated algorithm for telling if a number is prime in polynomial time. That's way beyond the scope of this course. Now let's talk about a different class of problems called NP. Even if you're talking about decision problems, you might be able to produce some evidence to back up the decision. For example, if you want to say that n is not prime, then what would be the evidence to back up the no answer to is n prime? You would show a number that divides n. You would show an I that divides n. And anyone could check very easily that proves, anyone can easily determine that I divides n, and it proves to them that n is not prime, right? So this I is a sort of a solution or a certificate of the fact that n is not a prime number, the factor of n. Because finding I is hard, but if someone gave it to you, you could easily check it. So basically, there are certain decision problems, and for these problems, when the answer is yes, actually, there is a very, very short certificate that someone could provide, that you could confirm, you could use to confirm that the answer is really yes. So, for example, for the problem of common subsequence, to prove that there is a subsequence between x and y of length at least k, someone could just show you a subsequence of length k between x and y, and then you would have to verify that that subsequence occurs both in x and in y. And you can check for yourself that this is not too hard to do. But of course, in this case, solving the problem is easy too, but let me give you another example. Here is an example of a problem for which we do not know a polynomial time algorithm. Given a graph, an unweighted, undirected graph, we say that a Hamilton cycle in a graph is a simple cycle that goes through all the vertices of the graph. So it starts at some vertex, visits every other vertex without ever repeating a vertex, and comes back to the starting vertex. That's the Hamilton cycle. So one decision question is, given a graph, does it have a Hamilton cycle? So this question has a yes-no answer. It's a decision problem. But no one knows a polynomial time algorithm for it. No one knows how to solve this problem efficiently. And if you actually solve this problem efficiently, there are many institutions that offer prizes worth several $1 million for the solution. So if you come up with an algorithm to solve this problem efficiently, you will be a millionaire. But anyway, so this problem is not known to be solvable in polynomial time. But think about the situation where the graph does have a Hamilton cycle. If someone who magically has figured out what the cycle is presents the cycle to you, shows you the sequence of vertices on the cycle. It starts in V1, goes to V2, goes to V3, to Vn, and finally back to V1. All you'd have to do is verify. So given that solution, all you'd have to do is to verify that every vertex in the graph is mentioned in the sequence, and that every vertex that succeeds another has an edge from the other one. So basically, every pair of successive vertices is connected by an edge. So if you could verify those two things, you would confirm that this is indeed a Hamilton cycle. So even though you don't know how to find a Hamilton cycle in a graph efficiently, someone could show you that a graph has a Hamilton cycle, which even if you don't trust them, you could verify for yourself very efficiently. So this is the hallmark of NP. NP is the class of decision problems where if the answer is yes, then there is some kind of solution or certificate that someone could provide that you could verify easily in polynomial time. So the verification is in polynomial time. And you don't have to trust the person providing the certificate at all. You will detect a fake certificate very easily and reject it. And you would only accept good certificates. NP stands for non-deterministic polynomial. And I won't go into why it's called non-deterministic polynomial. You just need to understand that the definition is that NP consists of those decision problems for which whenever the answer is yes, there is a short certificate that you can verify in polynomial time. Okay, an example of an NP problem is the maximum or a clique problem. So this is the decision version of clique, which is given a graph G and a number K, are there K vertices in the graph that are all pairwise adjacent? So if a set of vertices is such that every pair of them is adjacent, it's called a clique. And it's kind of analogous to the English use of the word clique, like a group of friends who are all friends with each other and who hang out together. It's called a clique in school, for example. So this is like a clique of vertices, meaning everybody, think of these edges as representing friendships. These are a set of vertices where everyone in that set is everyone else's friend. So that's a clique. So given a graph G and a number K, the clique problem asks, is there a clique of size K? Now this problem is also one where we don't know any polynomial time algorithm. And it's a useful problem. I mean, it's clear that something like Facebook would want to solve this problem to figure out, what's the largest group of friends we have in the Facebook network, or who all are friends with each other. So you could imagine various applications of this algorithm in social networks. But unfortunately, we don't have an efficient algorithm for this problem. So this problem is useful. But if the question is, does this graph shown here, and let's say K is 6, does it have a clique of size 6? Now, even though we may not have known how to find this clique shown in orange, if someone showed us these 6 vertices 1 through 6 and said, look, here's a clique of size 6, it would be very easy for us to verify this in polynomial time. All we have to do is to count that there are 6 orange vertices and that every pair of them is joined by an edge. Once we do that, we will accept, yes, this proves to me that this graph has a clique of size 6, although I couldn't find the clique myself, or at least I don't know how to find it efficiently. Another example is a 3 coloring problem. So you're given a graph, and what you want to do is to color the vertices of the graph with 3 different colors so that adjacent vertices must get different colors, do get different colors. So, so here is an example, and we've shown a coloring with 3 colors, blue, green, and orange, where you can check that no pair of adjacent vertices get the same color. Again, this problem we don't know an efficient algorithm for, meaning if you're just given the graph, it's very hard to come up with the coloring where you're using 3 colors and making sure that adjacent vertices get different colors. But if someone gave you this coloring here, showed you this coloring, it's very easy for you to verify that this is a valid coloring. That is, you can check that only 3 colors are being used, and that for any pair of adjacent vertices, the colors are different. So notice a slight asymmetry in all these definitions of problems in NP. We only need that there be a solution that can be quickly verified for the inputs for which the answer is yes. So if the graph is 3 colorable, or if the graph has a Hamilton cycle, these are yes cases. If the graph has a clique of size k, that's a yes case. Now, how do I prove that a graph has no valid 3 coloring? Now, that's a much harder problem, and we do not know how to produce a short proof for that can be quickly verified. So again, we only need to have short proofs when the answer is yes. That's what defines NP. Now, the 3 coloring problem is very important, for example, for assigning frequencies to radio stations or assigning registers to variables when you're writing a compiler and so on. This problem also arises in practice. Unfortunately, we don't know an efficient algorithm for solving it. One last example of a problem in NP is the partitioning problem. It's a very natural and easy to explain problem. You're given a set of numbers, like in this example on the left, you have these numbers 1, 5, 2, 4, 3, 7, and you want to know, can I split the given numbers into two sets such that each set adds up to the same value? Now you might want to solve this problem if you want to divide some valued objects among two inheritors equally and fairly. So maybe there's a value to each object. The first object is valued at 1, the second object at 5, and so on. And you want to divide these objects between two people so that they both get an equal share. You would want to solve the partition problem. And in this case, the answer is yes. If you look at it, the blue numbers sum up to 11, and the orange numbers sum up to 11 too. Now you can see that when the list gets a little longer, the problem gets a little trickier. I mean, this second list, we're not going to solve it for you. It's not too hard. But as the lists get really long, we don't know an efficient algorithm that's polynomial time to solve this problem. But again, it's a problem that's in NP, because if someone showed you a partition and said, look, this one works, that's the solution, you could easily verify that the numbers on in the two parts add up to the same value. So given a solution, it's easy to check that it's correct for the yes cases.